We're looking at a sequence here, and the sequence is a sub n equals 1/2 to the power of n. And what I want you to do is a quick review of calculating partial sums. So we've got this sigma n equals 1 to 3. Here we have sigma n equals 1 to 4. Here we have sigma n equals 1 to 5. So take a minute and pause the video and just to review that concept, calculate those quickly. Okay, I'm going to show you my work now. Okay, so there's my work for those three. Hopefully you got the same answers. Now, if you look at these numbers, do you notice anything interesting? One thing I notice is that the numerator is always 1 less than the denominator, meaning that these numbers are less than 1. And not only are they less than 1, but because the denominators are getting bigger and bigger, that means the numerators are also getting bigger and bigger, which means we are getting closer and closer to 1. So this is really interesting. You might be asking the question, well, how long do I need to add this sequence up until I get to 1? Well, feel free to give that a try and see how long it takes you. I'm going to show you a visual way of thinking about this as well while you're calculating. So, just calculate away, but here's what I'm thinking. So what we're really talking about when we talk about the partial sum of this sequence. So we're adding up 1/2 plus 1/4 plus 1/8 plus 1/16 and so forth, right? You might notice that each of these fractions is half of the fraction before it. Well, this makes sense because the whole point of the sequence is that we're increasing by powers of 1/2. So if we think about that in a picture, so I'll represent one whole with this kind of wonky looking circle here. So our first term is we start with 1/2. To that we add 1/4. So 1/4 is half of this piece that we've got left. So that's 1/2 plus 1/4. If we were to add 1/8, 1/8 is half of this remaining piece here. So that would be adding this little slice. Add 1/16, and we would be adding half of this slice. Now, hopefully you see what's going on here. There's actually something really interesting going on here if you start thinking about the concept of infinity. If we continue cutting this white open space in half over and over and over again, there's always going to be a little bit of white space left. And no matter how much white space is left, we can always cut it in half more and more. So the point is, this sequence, if we keep on adding all of these terms and you just keep going forever until the end of time, you'll get closer and closer to 1. This is where things start getting a little bit crazy. We're talking about infinite series here. So if you take the terms of a sequence and you take infinitely many of those terms and you add them together, sometimes you can actually get a sum. Now this is crazy to think about because you're taking infinitely many things and adding them together and you get a finite number. This is confusing for a lot of people, and it makes sense that it's confusing So don't feel like you're the only one if this is weird, because it's supposed to be weird. Now, interestingly, we actually have a formula for the infinite sum of a geometric sequence. This works for geometric sequences. So the formula looks like this. You can write infinite sum in a couple ways. One way you can write it is capital S sub infinity, so that means infinite partial sum, sorry, which doesn't really make sense. Partial sum is finite, but infinite sum. If you want to write it using the sigma notation, it looks like this. So we can have n equals 1, and we have infinity on the top of the sigma, and then we have a sub n here. And the formula is this. So we take a1, the first term, divided by the quantity of 1 minus the common ratio. So this is the formula. It's very simple. There's one important thing about this formula though, or actually there's two important things. So I'll mark those really carefully down here. So this only works for geometric series, which I mentioned already. And the other key thing is that we only get a finite sum if the absolute value of r is less than 1. If you try some examples where r is not less than 1, it will be obvious why this is true, but it might not. You might not have thought about that. So another way of thinking about this is that r is between -1 and 1. So we could also write this as -1 less than r, less than +1. Okay, so if you have these two conditions, that means you can apply this formula to calculating an infinite sum. So for example, I can use this formula to prove what we were looking at before quite easily. So as an example, if this is our a sub n, well, let's see, the infinite sum of that, the sum from n equals 1 to infinity of a sub n is equal to the first term. If n is equal to 1, the first term here is just 1/2 divided by 1 minus the common ratio. The common ratio for these terms is 1/2, right? Because to get from one term to the next, we have to multiply by 1/2. Okay, so then in the denominator, we have 1 minus 1/2. All right, and let's see, if we calculate this, we get 1/2 in the numerator, 1 minus 1/2 is 1/2 in the denominator. 1/2 divided by 1/2 is 1. So therefore, we get the infinite sum of our sequence an is equal to 1, which is exactly what our intuition told us in this picture here that we were drawing. We have 3 examples here where you might try to use the infinite sum formula that we just discussed. So I encourage you to pause the video and take a minute and try to solve these on your own before I explain them. Okay, if we take a look at the first one, And I'm just going to write out a few terms. So if n is equal to 1, we get 1.5. If n is equal to 2, we get 2. If n is equal to 3, we get 2.5. N is equal to 4, we get 3, and so on. Hopefully we recognize this is an arithmetic sequence, not a geometric sequence. So we cannot use the formula here. So not possible because it's not geometric. Okay, how about the second example? Well, we could again write out a couple terms here. So if n is equal to 1, we get 1/3 times 2, which is 2/3. If n is equal to 2, we get 1/3 times 4, which is 4/3. If n is equal to 3, 2 to the power of 3 is 8, so this would be 1/3 times 8, 8/3. If n is equal to 4, we get 16/3, and so on. All right, well, the good news is this is a geometric series. The bad news is the common ratio is 2. You have to multiply by 2 to get from one term to the next. So remember that formula only works if the common ratio is between -1 and 1. And 2 is definitely not in that interval. So this one is also not possible because r is greater than 1. Okay, well, hopefully this third one works. Otherwise, I just led you on a massive wild goose chase. So let's see. If n is equal to 1 in this formula, I get 27 times -1/3, which is -9. If n is equal to 2, -1/3 squared is 1/9. So 27 times 1/9 is 3. So now I add 3. Okay, if n is equal to 3, this is -1/27 times 27 is -1, so plus -1, and we could keep going. Now the good news is we have a geometric series, and the common ratio is that we are multiplying by -1/3 to get from one term to the next term. -1/3 is between -1 and 1, so it's a geometric series, and the ratio fits the criteria that we need, so that means we can actually use the formula. So therefore we can write the infinite sum is equal to the first term on the top, so let's see, -9, and on the bottom we have 1 subtracted with the common ratio, so 1 minus r is 1 minus -1/3. Okay, so in the bottom we have 4/3, because if you subtract a negative, that's the same as adding. So the infinite sum here is -9 divided by 4/3, which is the same as -9 times 3/4, which is equal to -27/4. Okay, so kind of a weird number that we get, but if we add up this term infinitely, infinitely long, if we keep adding and adding and adding for the rest of time, the sum that we would reach is this value here, negative 27 quarters. If you find the concept of adding series infinitely long, I really encourage you to watch this video that I link here from one of my favorite YouTube channels, Numberphile. It's a rabbit hole. It's not related to pre-calculus, but it is super interesting.